The radar system onboard the J-20 fighter jet is one of the most sophisticated sensor suites ever integrated into a stealth combat aircraft. To fully understand its capabilities, it is essential to examine the many layers of technology, physics, and design constraints that define its real-world performance. Radar technology fundamentally depends on the transmission and reception of electromagnetic waves. These waves travel at the speed of light and can be reflected off objects to reveal their position, speed, and size. The radar onboard the J-20 transmits pulses of energy that travel outward in a specific direction, scanning the airspace ahead. When these pulses encounter an object, a portion of the energy bounces back toward the radar receiver. By measuring the time delay and Doppler shift of these echoes, the radar system can determine how far away the object is, how fast it is moving, and its relative direction. This process is governed by the radar range equation, a fundamental mathematical relationship that quantifies how various factors influence detection range. The strength of the return signal is inversely proportional to the fourth power of the distance to the target. This means that if the target is twice as far away, the return signal strength decreases by a factor of 16. This rapid decrease imposes a natural limit on how far the radar can effectively detect objects. To compensate for this signal loss, radar engineers seek to increase the power of transmitted pulses, improve the gain of the radar antenna, and enhance the sensitivity of the receiver. Each of these strategies has limitations. The J-20, like all fighter jets, has finite onboard power. Electrical power is generated by the engines and distributed among avionics, propulsion, cooling systems, weapon controls, and the radar system itself. Prioritizing radar power comes at the expense of other critical systems or overall aircraft endurance. Furthermore, transmitting higher power pulses generates heat within the radar's electronics. The radar's transmitter and associated modules must be carefully cooled to prevent damage or degradation. Stealth aircraft designs such as the J-20 place strict demands on cooling solutions because they must maintain smooth external surfaces and reduce heat emissions that could reveal the aircraft's position. These constraints limit how much power the radar can continuously output. The antenna array size is also critical to radar performance. The J-20's radar uses an active electronically scanned array AESA, a grid of thousands of tiny transmitter-receiver modules. AESA radars provide rapid, precise beam steering without mechanical parts, enabling the radar to scan wide volumes of space quickly and track multiple targets simultaneously. However, the antenna aperture is limited by the size and shape of the aircraft's nose. Larger apertures allow for narrower beams with higher gain, improving detection range and angular resolution. But the J-20's stealth design restricts antenna dimensions to maintain low radar cross-section, reducing the maximum achievable antenna gain. Radar frequency choice further complicates design. The J-20's radar likely operates in the X-band frequency range, offering a balance between resolution and atmospheric penetration. Higher frequencies allow for smaller antennas in finer resolution but suffer more from atmospheric attenuation due to rain and humidity. Lower frequencies propagate farther but require larger antennas for similar resolution. Stealth features on the J-20 reduce its radar cross-section, making it harder to detect by enemy radars. This also means its own radar must detect targets with potentially low RCS. The radar's receiver sensitivity and signal processing algorithms are critical to reliably detecting weak returns from stealth targets. Environmental factors influence radar operation. Atmospheric phenomena like rain, fog, dust, and temperature gradients scatter, absorb, or refract radar waves, affecting detection range and accuracy. Variations in temperature can bend radar waves unpredictably, creating shadow zones or false echoes. Electronic countermeasures (ECM) challenge radar effectiveness. Adversaries may attempt to jam the radar by flooding it with noise or craft deceptive signals. The J-20's radar must counter these attempts using techniques like frequency agility, beam steering, adaptive filtering, and pulse compression. These methods make the radar less susceptible to jamming and improve its ability to discern genuine targets. Radar systems must track multiple targets in real time, updating positions and velocities continuously. This requires advanced algorithms that predict target maneuvers and discriminate real signals from clutter and false targets. High processing power and sophisticated software enable the radar to maintain situational awareness in complex, contested environments. Radar horizon limits detection of low-flying targets due to Earth's curvature. Higher altitude flight extends radar line of sight but is constrained by mission requirements and aircraft performance. Many tactics rely on flying below radar horizons to avoid detection. Overall, the J-20 radar is a balanced system optimized for stealth, power efficiency, and electronic warfare resilience. It is a significant technological achievement, but its performance is bounded by well-understood physical laws and engineering realities. Claims of unlimited or extremely extended radar detection range contradict these principles. While continuous improvements occur, physics and engineering trade-offs impose hard limits.